I'll just yeah. So basically, I'm just going to talk about kind of just a bunch of just different random things about microwave photons and circuit QED. So yeah. So I'll go a little bit through circuit QED things and maybe pose some questions there, and then I'll talk a little bit about the fluxonium circuit, and then maybe generalizations of that. And I don't actually like if we can, maybe we could mention some of these higher frequency things, but more as, again, sort of motivation for things to talk about. But okay, and okay, so you know, in circuit QED, as we've seen probably a couple of times, we're trying to couple superconducting qubit to a microwave cavity, and as Michelle just explained earlier, like we're actually one of the main purposes for that is just reading it out, although we can do all kinds of other things with it as well. And it can protect the qubit from the environment. And so, you know, we have our qubits that are like this. They're basically like a harmonic oscillator, except we have the junction, which makes it somewhat anharmonic. And then we have the LC oscillator, which can be our cavity. And you know, and then we sort of say it has this kind of a Hamiltonian, right? So we've got sort of the two pieces. We've got a coupling, and I've sort of identified the terms here. So and you know, the usual goal is to have the interaction, the single photon scale interaction, be much larger than any of the decoherence processes. And so we can, and you know, you can sort of think of that as just basically we have an atom with a photon. It can release the photon into the cavity. If they're resonant, it just bounces around for a while until it gets reabsorbed. And we want to see that happen faster than in the decay processes. So we can just, yeah, here's what it actually looks like. And well, actually one instance, it can look like a lot of different things, but this is, you know, you can see they look pretty similar actually. This is a coplanar waveguide resonator, and this is a qubit. And yeah, so we can have lots of different types. In particular, the qubits they can look somewhat different, but the cavities really can look quite different. So you know, this looks vaguely LC-ish, right, with like an inductor and something like a capacitor, but it could look like a transmission line. But these are all cavities. Well, I guess this one's not in our lab. This is a Tesla cavity in Fermilab. If Fermilab had their way, quantum computers will look exactly like accelerators with these cavities. But you can literally put your photon in a box. Like this is just a copper box that you machine and screw together, and it will live for a while. And if you make it out of superconductors, it'll live for a long time. You know, there's also, this is a three-dimensional kind of coax cavity. You can have also these sort of long waveguide cavities that we make in various different ways, and I'll mention them later. If you can really, one thing I like about this is the very first experiment you do, you can really just directly kind of observe this nice Hamiltonian. So if you make the qubit tunable by splitting the junction and making it a squid loop, you can, if you just tune the flux, you'll tune the qubit, and the cavity shouldn't care, and then and they'll cross each other. And whenever two coupled things are crossing, you see an avoided crossing, and the you know, you can actually read off all the relevant numbers here. So you've got both your qubit frequency, you got your cavity frequency. The splitting here is just twice. This is just twice that G. So if you see two lines, you're in the strong coupling limit. So that's good. This one was, again, this was actually designed for like readout or something like this. It wasn't designed to for doing coherent quantum operations. So actually these lines are kind of fat, which makes them easy to see. But we can actually, you know, the G's can be 100 megahertz if you want, or even bigger. And so if you want to take this one number that kind of does it, that kind of is the kind of overall kind of figure of merit, you can take this G squared over kappa gamma, which is like the line width of this and the line width of that. And it's really big for us. So it's like, you know, it can be over, I think it can even be bigger than this. It can be over a billion. And so that's good. And roughly, not everything, but a lot of things go, like the infidelity of like a gate that's mediated by this, or a transfer, or typically readout. A lot of things go like the square root of this number, basically. So if you know, so if you have a billion, that means you can probably get like 4 or 5 nines for a gate in principle, something like that. So that's when the things are unresonant. If you look here, they're actually still interacting, but not exchanging real photons. Then you're in this dispersive limit. So this term doesn't conserve energy anymore, and it becomes this. And you heard much more sophisticated versions of this from Michelle. But I just want to, so we use this to do a non-demolition readout of our qubit. And so the idea is just that, you can think of this as like, right, the thing that goes before the A dagger A is the cavity frequency. So the cavity frequency now has a sign, it's just by chi, but the sign depends on the state of the qubit. And so that's how we read out. You can read out on these peaks, or you can go in the middle, or whatever you want there. But you can distinguish between the two states. These experiments are nice because you can like just directly see the uncertainty principle in action. So so the same shift, right? Like you can think of this as the qubit frequency, which is just and now you can see that this is the photon number. So the qubit frequency should shift by an integer number if the field is quantized. So you can see that it is. I think sorry. So you have so they really are photons, right? There's the evidence, right? Like 0, 1, 2, 3, so on. We can really count them individually. And the thing I would also like to point out is that since like people are so adamant that the optical photons are the real photons, they really are pretty like casual in their disregard for their health, right? So aside from making these ultra strong pulses and then applying them to materials until they hit the damage threshold of both the material, of the materials, but they don't even talk about the fact of what happens to the photons. And if you measure a photon, an optical photon, you immediately destroy it, right? You're not actually measuring that photon. What you're doing is you're using that photon to knock an electron out of a semiconductor or break a Cooper pair, and then you're measuring that electrical signal, right? So the photon is gone by the time you've measured it. And I think that is one of the challenges with optical, like these heralded optical quantum computers would be a lot better if they didn't have to, every time they measured a photon, it didn't die. And in our case, those, we can tell that the photon's there, but it's not that like we're absorbing like the energy and then this is that energy. This is a tiny little shift. So we're dephasing the photon a little bit. We're changing its energy a bit, but it's still in there bouncing around. It's it's sort of almost more like the radiation pressure situation, although it's not the exact same Hamiltonian. So we can really manipulate these single photons, both count them, measure them, all this kind of stuff. So that's really nice. And again, it's very difficult to get these numbers in optics. I've been thinking, we've been thinking about why that is for a while, because I've spent a lot of my career just sort of saying like, well, like that optical cavity QED is really great. Like, how could we do various things that people have, either done or more recently like dreamed about doing with our system. And so that's how I got my start. And then more recently, I like to argue with John Simon a lot, and I guess even more recently Amir. But most of my arguments, the ones that date back, go with John. And so we've discussed this for a while. And the basic fundamental reason is actually that atoms are small. They're an angstrom or so, and photons are big, of order of micron. That's also the reason atoms are so great, is because they're kind of small and stiff. That's why they have such nice properties, and why all the frequencies are high and they're very stable. But it is challenging then to do it because you kind of miss most of the time when you have a photon. And so what people tend to do is they have a cavity to kind of recycle the light, as we heard in other talks in the kind of solid state context. Most people actually, so this is they use, instead of C, they use eta, but it's the same cooperativity basically, and you can write it in terms of more optical looking parameters. Actually, this is actually a weird way of writing it. I think even in that community, most people write it as instead of finesse, they use the Q, and instead of kind of the cross-sectional area, they use the volume of the cavity, which is kind of the same thing. But actually, the reason we've started to write it this way is because it actually it sort of in a lot of cases it's the same, but it kind of belies a thing, which is that which people may know, if you have like a resonance that is overcoupled, whether it's an atom or electrical resonance, then on resonance, if you drive it, its cross section is lambda squared. Okay, this is sort of the thing. And so this is really made evident by the way you draw this here. And so you have the width of the waveguide, and then the atom is basically, it looks like a lambda squared kind of object. And then of course you have to take out if you went from volume, you take out the length, and then the Q comes with finesse. The microwave people are like, what are you talking? Are those the same thing? But actually, these optical cavities are very long usually compared to a wavelength, although they can of course be small. And so and so one thing I hadn't appreciated, I always had just assumed that like these beams got to of order a micron because that's the diffraction limit. But as it turns out, as I'll show you in a minute, like it's actually quite hard to do that. And so they tend to be around, even people who are trying can get to typically like 10 microns, or it's usually even more like 30 microns. And remember that, and this goes like the square. And so you actually have to, and so to make up for that, you need a lot of finesse if you want to get over one. That's why optical cavity QED is hard to get like reasonably high coercitivity. And an interesting thing is, another thing that's sort of different is like in the solid state, we're always worried about materials and losses and dissipating to phonons that we want. Actually, that's not an issue for an atom, but the thing that gets the atoms is 4 pi. It's just space, right? So this cavity actually, it looks kind of, you can kind of see it a little better here. If you look at the mirror, and whenever I've seen pictures, I really hadn't realized this until fairly recently. It looks pretty big. It looks like you should be getting a decent fraction of 4 pi. But if you look at the mode, you can see actually it's a very small fraction, and this is still a cartoon. It's probably worse than that. So basically, most of your finesse is essentially, right, is to essentially make up in spectral density what you're lacking in spatial density. People, of course, have tried to improve this in a couple of ways. So you can try to get the smallest waste you can in a conventional cavity. People then also go to these fiber cavities, which is basically still just a nice way of making a small version of this. And you can even do like photonic crystal cavities like the ones that we heard about, but just try and trap an atom near there, which is really heroic. But you can try and do it. So people have had various levels of success with all these things. I think you can get like single atom cooperativities around maybe 10,000 now, something like that. So it's like with atoms, it's not bad. You can still, certainly they can show all the stuff that I showed before. John and I have been looking at, and mainly John and his group have been pursuing kind of a different path, which is, again, if you take this formula seriously, then you say you really want to have a tight waist, even at the expense maybe of some finesse. Actually, when we were visiting here, when we were they're kind of showing us around, we were talking with Mark Kasevich, and he has a microscope where he just put like a very low Q kind of cavity on it just to kind of enhance it a bit. And we're like, well, I mean, why can't we do that? We sort of thought about that, and it turns out that, so I should say the reason why basically people have this is our curve. So these cavities have this curve where basically they're stable in the middle. If you go to one side, basically they become flat, and then it's like this hall of mirrors. And if they're not perfectly aligned, the cavity becomes unstable. If you make it like confocal, then what happens is all the modes mix together, and you get and it becomes unstable in that way. So that's why the two places where you can get a small mode are at these two edges. So if you have a conventional cavity, this basically happens by the time you're at like the 10 micron level. But with the lens, basically, it kind of stabilizes things even pretty close to the diffraction limit. So you can maybe go here and still be fine. And since now the wavelength, this the lambda and the W are now, so the focal spot is L over F squared. So if you have like an A sphere or something where you can have a tight focus and high NA, then you can basically get a pretty small spot, and then. And now you actually don't need we put a lens in here, and so the finesse is not great. Like we get like a finesse of 30 or 50 or something like that. But even with that really low finesse, you still get like strong coupling. And this is, again, cooperativity is only like 1, fairly strong coupling, but you can certainly see that it's 2 peaks and it's a single atom. And this is like, finesse here is like 40. This is really like the very first version, and like we have like a list of things we know we're doing wrong. In fact, this cavity, so you can do things that are like would be crazy if you in a cavity you're trying to make high finesse. So for example, this cavity actually involves the like somewhere over here, it actually involves the vacuum chamber window, and so yeah, so you can now think to put stuff, because if essentially if you have a high finesse thing, then your whole experiment is built around keeping everything high finesse. But if it's low finesse, you can kind of be sloppy or do other things or push other things. So it's kind of neat. And one application, like with our stuff, you can use it to read out qubits. One of the things that's been limiting the neutral atom experiments is the readout time, which has been many milliseconds currently. And here, again, sort of in this very first pass, we're already at like 100 microseconds. And we should, and you can see that this is 10 megahertz. So I mean, we should be able to get to, better than a microsecond in principle. And so, yeah, so that's a nice approach. And I think, again, it kind of, it has, well, it certainly is, it's the macroscopic version of trying to get the cross section of your waveguide down, I guess. We don't have the temporal parts. That's an interesting thought there. If you wanted to really make this scalable, it would be nice to have not just, the cavity is still kind of bulky, so you would like to, but you want to have it work for a lot of atoms. So it turns out if you stick a micro lens array in the right spot, you can actually image, instead of having one cavity, you have actually a whole array of cavities, and they can be on the kind of the same scale as your tweezers and stuff like that. In fact, you can even catch, you can actually use those as traps, so they should probably be more efficient. So again, I think that's kind of an interesting direction. And then I think one particularly interesting direction would be actually to do quantum networking with this, because you have this array of atoms, and you can just get them all out. But for example, atoms, they have a lot of transitions. If you use the right atom, you can usually find some transition that might be near the telecom bandwidth where you can use all of the amazing photonics that we've heard about. But let's say if you take rubidium, which is the one that people like a lot because it's simple, that the workhorse transitions at 780 nanometers. But of course, you can just do like kind of the macroscopic version of these kind of interactions where you just have a bulk periodically pulled crystal. And again, putting that in a high finesse cavity would probably ruin the cavity, but since it's actually, it's not even really the limitation in a cavity like this. And so you can then just kind of put a pump tone in here with a dichroic mirror, and which can also be in the cavity, and then you can convert it. And I think this wavelength isn't particularly special. It was just like that was the pump we had lying around. So we could do it into a telecom or whatever. In fact, we have like similar idea. And the other thing is that if this is a dichroic mirror, then basically you don't have to act. It can go around a bunch of times, and you can use this to make a variable outcoupling as well. So you can actually tune your cavity this. And I mean, this is actually not so different how many lasers kind of work, but we can now do this in sort of a quantum context. So I think this is a really exciting kind of direction there. And it would be fun, again, to sort of go back and forth between the microwaves and this, and also, what can we, are there ways, either things we could, that have been done in the integrated photonics community that maybe wasn't viable before, but maybe we could do it here, or vice versa. And so just some questions, it says like, why is the cooperativity so high in the circuit QED? Well, it's basically because like, there isn't really an atom in a cavity, right? They like look like, if you didn't know better, you would say these are the same thing, right? It's just two circuits, and they're two macroscopic pieces of metal. In fact, like this capacitor couples them, but it's totally arbitrary. If I wanted, I could just connect them, right? And then it would be 100%, right? Or, I can, and I would just be picking like the wrong basis or something. So on the one hand, so in some sense, G really is just like the Q, in some sense. If I want to take I can say the G can always be 1 if I want it to be, and so I should just make it that. And so it's just sort of saying that. And you might ask, like, is it cheating? And I would say it isn't. Even so, it's not cheating. I think because the like maybe you should say, well, I don't care about the linear stuff because that's just normal modes, but maybe I care about the nonlinearity, but our nonlinearity is also kind of like 100% if we want it to be. So we can, in a transmon, it's 10%, but if we in fluxonium, which I'll show you, it's going to be over 100%. So I think it basically ends up, it's still a meaningful thing in terms of like how fast you can do a gate or what the error on your gates might be. And I think it's also useful because like, it means that we can go from this junction that is much smaller than the wavelength of light, even more so than the atom is compared to an optical photon, to macroscopic stuff, even like as big as this, and still do that pretty efficiently. So I think it's again, John and I like to talk about this, and I think it's basically in some sense that the superconductivity interaction is large, or the interactions between the photons in the modes are large. And okay, so I wanted to show some fun, processes that we can do with these things and ways that we manipulate light. So we can, so I told you how we could detect a qubit using light. We can also how we could also detect single photons using a qubit. We can also use a qubit to make single photons. So this is a Rabi oscillation of a single photon in a linear cavity. But what we do is we have a qubit, so this way it's kind of the qubit, and we basically use a process which, I mean, will be familiar. It's like a three-wave mixing type process, which basically takes two photons out of the qubit and puts one photon into the cavity, and is activated by this drive. So it's four-wave mixing, but with a I don't know it's a three-wave term, but it's four-wave mixing. So that's one way of doing it. There are other ways of doing it as well. The other way that people have done is to take advantage of the same kind of crosshair, which is that shift I showed you at the beginning. And so if you combine being able to manipulate your qubit, or displace your cavity and these Kerr effects, you can show that that's universal. It's actually I think there's a constructive proof of how to do it, but it's pretty inefficient, and so you tend to use optimal control methods. But it works all right, and you can basically control things on this order of chi, which can be megahertz or so. And in fact, Michel had this really interesting series of works where he showed that you can essentially, even with a really tiny chi, you can kind of parametrically enhance it more. And that's another question again, is like, how much can you do that? And it kind of relates to some of the things that Michael and Amir talked about, and maybe also this question about what is your real number that you should think about to figure out the limits. I'll show you one just because it's a weirder one. I don't even know what to put here exactly. Maybe someone else has a good name for what kind of term. It's kind of a composition of terms, but what we can do is make a photon blockade where basically you can displace it and it's a totally linear object until it hits this barrier, and then it can't move anymore. So the way that works is that, remember I showed you all those peaks of the qubit spectrum. So imagine if you drove one of those peaks, you could do a number selective qubit oscillation. So now imagine you drive one of those. That splits the qubit, but it also splits the cavity, but only when it has that many photons. And so if I look at, so this is, let's say, the two cavity levels. So I'm driving here. So I only hit this line. I don't hit any of these other lines. But I've split the line. So everything is harmonic here, here, here. But when I get to there, there's no line there because I split it, or I could shift it if I want. And so here's just an example where we did this for two photons. So for one photon, for two photons, you can kind of see it just looks like a coherent state until it kind of hits that wall, and then it kind of warps around, and you can see the Wigner function is a nice two-photon state. It doesn't exactly do this if you just displace it. You have to use some optimal control if you want to get it just right. But for one photon, it does it. And this was a nice paper, actually. Previously, so this effect was actually demonstrated in 2015, but we did a version actually with a multi-mode cavity, this cavity, in fact, where actually you could have multiple modes. And so this effect, the qubit was kind of coupled to all the modes of the cavity. So if you stick the qubit like here at the end, it's going to talk to all of the modes of the cavity. Again, you could just think of it as a long waveguide where things are bouncing around, but we kind of think about it in this normal mode picture where there's just a whole bunch of modes there, and we use maybe just a few of them. And so the qubit actually is taking essentially the sum of all of the shifts from all the photons. It doesn't know about where they came from. It just knows that it's been shifted. And so if the shifts are kind of the same, and you do the same thing, it doesn't know which cavity the photons are in. And so then again, you can make something that's a blockade, but that is inhibited. So that means you have these cavities that are like not interacting at all until they, they hit n photons, and then all of a sudden they have like a brick wall interaction. So it's kind of, it's very like weird thing from like a many body perspective. And I think, and you kind of get this by composing these interactions. So that's maybe another, maybe we could discuss at the end about like, what are there any, if you know what you want to do, are there optimal ways of doing that? If you, are there, and what kinds of interactions can you construct that way? We have this fun technique about how we make it, where we basically, you can see it looks like we call it a flute because it looks like Swiss cheese and you can see through it. But actually it has a, even without putting a cap on it, it has like, it should have a Q of like over 1 billion in terms of radiation loss. And it's kind of, the idea is and it's made out of a solid block. So the idea is you drill from the two sides, and where they overlap, there's kind of a continuous waveguide. But to get out, there's only like a small hole that's evanescent. And so these are the modes. You can engineer, we do a little bit of dispersion engineering. You may notice that it's very even, which I don't know if that was a wise choice, but we can adjust the dispersion. And the T1s are, the lifetimes in these cavities are pretty good. If we really mess it up, it's like 100 microseconds, but it can go, and we can get 1 or 2 milliseconds, not too hard. We've made things, single mode cavities in niobium that are already tens of milliseconds, and if the Fermilab people have gotten things that are over a second, so it can last a pretty long time in principle, and it's also very stable, and we're thinking about all the different things we can try to use these things for. One thing might be as a quantum memory, and we have some experiments. I didn't have time to do it justice, so we won't really talk about it, but you can imagine that each one of these modes could store a qubit. And that qubit, because it's just an oscillator, it could be a 0-1 Fock state. It could be a cat. It could be a GKP state. It could be a dual rail type qubit. I mean, whatever you want. And so that's kind of a fun direction we're going, and it's working pretty well. And so kind of some questions there was kind of I was like, so we talked a lot about cooperativity, and like, what is the cooperativity of lithium niobate? I don't know if that's a well-posed question or not, but like, you could sort of think of the atom as like, I don't know, the unit cell or something like that. But I don't know how to, I don't know exactly how to phrase that, but it would be nice to have some kind of a metric like that. Another question, like, because I hear all these proposals which usually involve a lot of post-selection and things like that, and for optical quantum computing in particular, and of course, we also are we're microwaves are photons too, so we're also an optical, or not optical, but a photonic quantum computing modality. And so is like either is that the right metric, or if so, then how much do you really need? Like, it seems like the targets are actually lower in the optical community than that, and that's partially because, like, I mean, obviously you should get to 1 or 100 first, and then worry about getting better. But they seem like they think that if they can just get there, then everything's golden. So if maybe there's things we could learn, or vice versa. And then again, one thing I've really noticed in so far in here is that everybody really thinks in this sort of time and spatial domain for these pulses. Yeah, wrong. Well, yeah, but that it kind of it's the ratio of the rate at which you can kind of do a gate, in some sense, the G or the nonlinearity, and the time you have to do it. So if you take and it's squared just so that you don't have a square root in it, but like if you take the square root, that's roughly the likelihood of having a loss event during that time, or a phasing event. Yeah, well, that was sort of what I said before. Like, it's not totally clear that you should use the G. Maybe you should use the anharmonicity as instead of G, which they're not that different, right? The anharmonicity is like 200 megahertz. G is typically 100 or 200 megahertz, or even less. So, I mean, it depends on what you're trying to do, but yeah. And then, yeah, and so I think, anyway, it seems like there's a lot of interesting things that happen, especially if you're kind of in a longer type cavity, if you can actually spatially compress your pulse, or think about it as a time domain pulse. I think like in this case, the way to think about it would be like, I could either think about my modes looking like this, or I could think of a pulse. If I, had a large superposition of these modes, it would look like a pulse that's moving back and forth. The qubit is in one spatial location. So actually, if I write the G of a superposition, it's going to scale like square root of n because it's really local, and it's being diluted by the fact that it's spread over the whole cavity. But if I made a pulse, I would get the full local G. So again, I don't know if there's things there. Okay, so I wanted to talk about fluxonium, which is another type of qubit. So the other one was, should be very comfortable for people because it's just a slightly anharmonic oscillator. This one is, this one also is like an oscillator. So the phi squared and this, and with a perturbation with a cosine perturbation. So it's not that different, but but we can now make this. We can change the kind of phase of kind of this this potential in this one, and so we can get to the degree. So I actually had, there's not that many fluxonium papers yet. So I got at least a decent fraction of them and just like plotted all their Hamiltonians and just made a little animation. So you can kind of see some of the variety. And with the transmon, there really is, either you're a Cooper pair box or you're a transmon. But once you're a transmon, there really is nothing else. Like it's just a matter of degree. Like the dimensionless, there's nothing that really fundamentally changes except the number of levels that are insensitive to charge noise. Here you can see there's a lot of stuff going on. You can go from being more like parabolic to having this sort of degenerate ground state. I'll do one that's not moving in a second. But you can also have things that have these extra side lobes, and you can imagine there's actually a whole phase that it looks, there's coherent Ising like things going on. There's a phase transition like things going on. It's already quite interesting, even just the single qubit. And I should also say that this was, I remember when this happened because Vlad was in Michelle's lab, right across the way. So it's not actually, this came out about only a year or two after the transplant. So it's pretty old, and people have done a lot of nice stuff. I think people are starting to really think about it as a qubit. And you might say, well, why? I mean, the transplant's pretty good, and it is pretty good. It works pretty well. But I can give you at least a flavor of an argument about it, which is that so the frequency is much lower. So I mean, we have, I think, the lower. We've been playing with the lower end because it's just fun to go to different regimes. So we went like, how low can we go? We made one that was like kilohertz. We made another one that's 10 megahertz. This kind of slowly creeping back up, but this one was like 50 megahertz, which is about the gate speed of most transmon qubits, because they have to be a little bit less than their anharmonicity, which is like 200 megahertz. But you can see that the anharmonicity is like 5 gigahertz actually. So and so in some sense, all the decoherence mechanisms are going like omega, but which is now much lower. It's 50 megahertz instead of 5 gigahertz. But the gate speed is actually going like we also made like ultra fast, at least on this scale, gate. So ultra fast for us in this case is like 50 megahertz, and we could do gates, and actually we could do it in a fraction of a Larmor period. But to make life easy, we usually do it in to avoid these envelope stuff. We usually do it in like 4 cycles or something like that. That's maybe a big argument. There's actually an interesting scaling of the matrix elements in principle also, which says that you should win like, well, if you had 0 temperature, it actually would go like omega cubed, almost like an atom. Most superconducting qubits actually only go like omega in terms of their the decay. So, but that's why hyperfine states are so long lived. But this one actually does go like omega cubed. If this is less than KT for us, so it actually that kind of kills one of them and replaces it with the KT. So, but it still actually is favorable. Like the lifetime still scales with omega, although we're not sure if we actually get that because of the materials stuff comes in, and so the Q of the material we were using may end up being worse when we try to make the thing smaller. Anyway, it has this rich level structure I showed you before, but it doesn't really require reset initialization in a surface code or error correcting code. It really requires good measurement. It's sort of the same problem as the measurement problem. So you need good measurement. The fluxoniums can do lots of things, so they're qubits, right? But actually, so this is a fluxonium, and this is a fluxonium, these 2 purple things. But this or blue thing, this orange thing is also basically a fluxonium. You can see it's the same components, the C and L, J. There's a common mode that's like more like a transmon, but it's far away. You can kind of ignore it mostly. But you can think of this as like a variable inductor, basically. And so we can use this as like a tunable coupling. And again, I probably should have put a reference here. Michelle and Angela Ko kind of did the version of this, which is static, where you just have an inductor and you can get nice coupling there. And it looks like this. Basically, if you split it and put a junction, you can now make it tunable. And so again, the qubit part of it, they're both the same basic Hamiltonian. The qubit part looks like this. The coupler looks something like that. And we can get and it's much higher frequency, so we can basically tune the interaction, and we get something that looks almost like a some kind of like a transverse Ising model type thing, and we can use that to actually drive gates between the systems. So if you just if you drive on any of these transitions, you'll get oscillations essentially. And if you do this one, it's an I swap, like Michael was giving us all the different ways you can do this. You drive on the outer one, it's a D swap. Normally, the I swap one is just as normally the I swap one tends to be faster because it's a lower frequency, and so you don't have to modulate as much, and you don't have this sort of Bessel dilution that we learned about earlier. But actually, in our case, the limit was actually just that it's pretty close to the qubit frequencies, and so we had to kind of watch out for that. Whereas this one is farther away, so we could actually just go. We actually could go faster. And it's actually so it's only a few Larmor periods. It's a very fast gate in that regard. If only we could do that in optical, it would be like an attosecond gate or something. Anyway, so we can use this as qubit, and the gates are very good. They're like 3 nines for this one, and they're pretty stable and stuff like that. So anyway, so you can make a good qubit out of it, and also a coupler, and so that's pretty nice. Mazar will tell you another, he'll tell you about probably these ATS and CAT stuff maybe, and that's also kind of like a fluxonium, but with a tunable EJ and used in a special way. You can also make he'll tell you about CATs that you can create dynamically with them. You can also just use the fluxonium as a CAT in some sense if you just change the parameter regime, and you can get very long lifetimes there. This was done by Johannes Fink's lab in IST. You could think about doing stuff with this as well. I saw that there's this paper. I've been thinking about this for a while, but never did it rigorously. I think Michelle has probably also thought about this, and I'm sure he's thought about it much more rigorously than I ever have. But I don't know if he wrote it down. But Luyan Sun just put out this paper on the archive recently. I forgot the reference. I'm sorry, but you can search it. Where you can kind of extend this idea. So this is the fluxonium. If you add one more junction, you can make an ATS. If you keep adding more junctions, you basically get like kind of a Fourier series, a Fourier cosine series, both in the phase variable and in these external fluxes. And so if you kind of vary the number of junctions as you do this, you can essentially you can make almost an arbitrary, once you do this angle addition formula, you can make something that's sort of vaguely arbitrary in both the flux transfer function and also the actual kind of dynamical phi variable. And so I don't know, this seems like a really special thing. This paper is great. You should read it. I think they were doing it in kind of a perturbative limit, and most things that people have thought about are in that limit, but it could be interesting to go beyond that. Here's just some more things that some of which we've done in our lab, some are other people. So you can use these kinds of processes to do autonomous error correction. So my student just defended 2 days ago, and he did this kind of autonomous error correction between 2 qubits. It's kind of like an autonomous cat code, but with transmons. And it involved all kinds of crazy stuff. Like there's this GG to FF, so that's like a 6 photon interaction, which was composed by 2 photon interactions, sorry, there's a 4 photon interaction. Sorry, and we can stabilize things that way. So that's one thing you can do. There's this very nice paper from Seclé, where they were doing. They made a different kind of single photon, more of like a clicky kind of single photon counter. And again, this was just using essentially that same sideband process I told you to make the photon in reverse, but using a second object to kind of as a way of like removing the entropy to stabilize it. So that was really a wonderful paper, and they've done some amazing single spin ESR using it. And then, of course, Majer will tell you more about this, but you can make a 2-photon dissipation, and you can stabilize things that way. And so there's a lot of things that we can do with all these strong nonlinear areas, but I think we're still just scratching the surface. How are we doing on time? I mean, I could also just stop here if people want to talk, because I mean, or I'll just go quick. So basically the millimeters. So anyway, so millimeter waves, we've been, so we went really low in frequency. We can all go really high in frequency. Also, you know, if you're clever, you can just find new things. If you're not as clever, you can just go in new places and hope you stumble on something. So it's been an interesting adventure on the just even the classical measurement side, and we've just been sort of going through all the elements. So we made cavities, and we can make decent cavities. Like the 3D ones can be like 30 million, and the 2D ones are a few 100,000. And we can make parametric amplifiers that at least have gain. We haven't really qualified them to be good yet, but they should be fine. And then we also wanted to make qubits. For that, we need junctions that work at these higher frequencies and higher temperatures. So we made this kind of a new flavor of this, what's called a niobium trilayer junction. Basically, everybody uses aluminum and aluminum oxide aluminum as the sort of Josephson junction, because that one is very robust and easy to make. But niobium would be better, but the oxide isn't good enough, essentially. And so there was already a process for this, but it tended to have low coherence. So we just tried really hard, basically, to make it clean, and we were reasonably successful. This is an okay time for a qubit, not state of the art, but you wouldn't throw it away, and you can do a lot of good science with it. And what's nice is that time stays good all the way up to, like, we actually extended this. It goes to about a Kelvin or so, and whereas aluminum dies at around 100 millikelvin or so, 120, 150. And then once you do that, you can also think about going to higher frequencies as well. So we made a qubit that actually works at like 75 gigahertz. And it's not that great. These are nanoseconds now, but I think, again, we've made better stuff. So we think we can improve that as well. And we didn't even bother with the dough fridge for this one. We measured it in a pumped helium-4 fridge. So it works. So maybe that's part of the reason it's not as good. But anyway, of course, I didn't do any of this stuff. This is all done by the students in my lab. I'm really happy that this was, now our group is here at Stanford and all together. So I think I think there's just like a lot of opportunity, from all the amazing ideas here and just in general. And so I'll just end with these more questions, and you can talk.
Hey, got some time for questions.
Very, very nice review. David, you introduced this idea that the square root of the cooperativity is in the end the limit in the fidelity of the gates. But you also said that the transmon had basically had only one parameter, which is true. It's in a sense. So when you try to optimize the circuit for getting the best performance for the gate, the best fidelity, you have to, there's this delicate moment of calibration. So the transmon is easier to calibrate than the fluxonium. Have you thought about this? What do you think about for when you calibrate a gate in the fluxonium? Don't you have to learn many more things?
Well, yes and no. So I think certainly, and obviously there's a lot of transmon gates and a lot of fluxonium gates. So it's depending on which scheme you choose. But like, for example, Google, for example, is famous for their calibration and all the different things. And I think the reason for that is that you have a lot of weakly anharmonic oscillators. They're still very nonlinear, but they're they each have a bunch of transitions within a few hundred megahertz of each other. So there's just a lot of transitions and there's a lot of coupling. So there's like kind of this combinatorial explosion of things, right? So then with the fluxonium, there's sort of at least, well, I mean, if you're making it flux tunable, it's not that different, but like you have at least one knob that you have to do, although in principle, or at least what we would have liked to do is just go to 1/2 and stay there and then have a dynamic modulation of the coupler, which I think we could probably get to eventually. And so that's pretty nice because even though everything is low frequency, it's order unity. Although that also has issues with crosstalk in a different way. But at least there's only the one transition because it's more like a real qubit because the next stuff is several gigahertz away. So there's less stuff. So we found it's actually in some ways easier to design a scheme that works with the fluxoniums because there's just less crosstalk, which tends to be the thing that gets you at the architecture level rather than necessarily the number of knobs you have to tune. But on the other hand, yeah, but I don't think it's clear. I mean, the transmon is also very simple and nice. And, maybe what I would say is I think any of them can work. I think the numbers are actually pretty good for all of them. But.
2 questions. Do you worry at all? First of all, you talk, and Michelle's talk was the same. You only talk about cross-phase modulation. Is there self-phase modulation?
Yeah, so,
and is it comparable? Or is it, like in optics, it's a factor of 2 different?
Yeah. So the way to think about the cross, so yeah, I should have said, so the qubit, right? It has that like cosine term, and then if you expand it to 4th order, that gives you a self care effect, and that one is pretty big. It's like 10% of the omega, which is limited not in any fundamental way, but because we want to avoid charge noise for technical reasons. But let's say it's a few hundred megahertz out of a few gigahertz or something like that. And then you couple, just linearly with like a linear coupling to, to let's say a cavity or to another qubit. And so then, that nonlinearity spreads, throughout the normal modes, to the other thing. And so then you get like kind of a 2nd order version of that. And so, it kind of goes down so if you have a coupling between the 2 objects, that's like G over delta, it kind of goes down like G over delta squared or something like that. So it's basically actually, so just typical numbers are like 100 megahertz for the self for a qubit if you want it to be nonlinear. And if you have a linear object that's coupled to it, then you get maybe you can get as much as a few megahertz pretty easily of crosscare. But if you want less, you can make it less. If you want more, you can of course add nonlinearity more explicitly. And we're often trying to get that crosscare without getting too much self-care. We want it to be linear. And of course, for some schemes like what Measure may talk about, you need like that's like a really hard requirement, and you go to like pretty creative lengths to do that, and it's possible. So it depends on what you want, but that's how it typically goes in these systems.
And also, I also haven't heard any discussion about instabilities. And, as you have a highly nonlinear system, and invariably, you can do all the steady state analysis, but it may be meaningless because you have all these instabilities. But I haven't heard much discussion. Are they there, and you just how to avoid them?
I would say that both Michael and Michelle's talks were basically, in some sense, exploring those instabilities, right? And so there are a bunch of them. Right. So if you do readout hard, this was one of the kind of original mysteries, and it seems now that it's kind of understood, and that does it. And as Michael said, in some sense, any kind of driving, whether you call it readout or not, if you drive it hard enough, it basically first it starts to leak into other states, and then it just goes chaotic and goes nuts. So yeah, that definitely it is like it's a Duffing oscillator. Like it has the opposite sign, but it's the same thing you showed in your first talk. Your first slide.
Concerning the instabilities, in fact, at the beginning, in the Josephson bifurcation amplifier, we were using these instabilities. But in fact, when you look at the time, the transition time in these instabilities, you find that you lose speed. So if you, for instance, if you want to make a good readout, which is very fast, actually those instabilities are not that advantageous. They will keep the memory, but in some sense, you have to reset the system to the other state, and that consumes too much time. So this, in some sense, we have moved away from exploiting the bistability.
I mean, all the paramps have this critical slowing down, and that's just assumed, right? We do the impedance broadening to get around it. So we impedance broaden to get around the steady state slowing down feature in the modern cavity-based paramps, but we don't tell you how long it takes to ring them up, right? We don't typically go past, as Michelle says, the instability anymore, but in the paramp, it's just sitting there. You can turn it off by doing this thing, simultaneous gain and conversion. In some sense, that's the better paramp. Now you get the full, more or less, bandwidth of the resonator at all times. The problem there is the instability is super handy because you get divergent amounts of gain at finite pump power. When you remove the instability, you get a linear gain, right? We saw 50 dB parametric gains, right? We do that because as you crowd in on the instability, you can get arbitrary gain. We can get 50, 60 dB too. When you remove it, 10 times more gain is 10 times more pump, which even for us is like fridge catch fire. So I think the one place we keep and exploit the instabilities is in the paramps. In the gates and stuff, we want, I guess what you call it, instantaneous response. So we're going to try to stay well away from them, though. Like Dave said, like they still in the end lead to us. I mean, we call it blowing up, we call it death, we call it ionization, boinking. Like you can see that there's a, Michelle calls it mist, but they're all still there.
Can I ask just like a weird technical question about the high aperture cavities with the lens inside? Just, thinking back to the old days of cavity QED, there were a few things that we always kind of wondered about or sometimes saw, but never really understood. So one is just this idea that when you go to that very high aperture with a high lens, there is some limit, right? Where, what your atom wants to interact with is a vector spherical dipole. And there's a limit to how well you can actually match that, right? By just focusing with the near spherical lens. So I don't know if so maybe the question is, how straightforward is it to predict numerically what your G is in those high aperture cavities from geometry?
Yeah, I think so. I mean, and I know, and again, John could better answer these questions, but I think so. I think certainly, like if you have a spherical mode, then as you get smaller, then you have this problem again. And so the aberrations are the thing that kind of kills you on the one side of things. So so having like an A sphere does that, and that gives it to you over some range. And eventually, we hope to do like more of a compound objective to get it broader.
But I think there's also a polarization thing.
Yeah. No, John has talked about it, and I think he has calculated it, but actually I'm not sure like where that gets you. But it definitely has come up in meaningful ways.
It's neat to be in that regime. The other thing is, we never, or at least in my time, we were never really able to approach 100% homodyne efficiency in measuring the light that came out of these really small cavities. And we never really understood that, except just imagining that there's some weird thing that makes the light coming in and out of these micro cavities, even if they're Fabry-Perot, they're actually not Gaussian beams. Do you run into that with?
Well, yeah. So one thing, like in these cavities, because they are high NA, like even like the next transverse mode clips, essentially. And so like, I mean, like, especially when you go to high NA, like you're going to, I mean, it shouldn't be such an issue with the Fabry-Perots, I would think, but certainly here, that plays a role. In fact, it may actually help because, like I said, one of the limits where you run into trouble is when you start to actually mix modes. But if, in some sense, if like the next mode is like terrible because super broad because it's clipping, then basically it's very broad and you get almost like emotional narrowing kind of effect, and so you actually couple less. And so we think like I wouldn't say we've like fully understand all of those effects, but like actually they definitely are relevant. I mean, another thing is like eventually we'd like to get it into a fiber so that we could like put it into all these photonic things and right, the Gaussian mode isn't actually the right mode for the fiber, and you can do pretty good. I mean, obviously they have nice lenses to do that, but I think we can actually use some of these cavity QED tricks maybe actually even get that up to 100% or close to 100%. And so I think that could also be pretty fun. Yeah.
Any last question? Okay, well, maybe we'll thank Dave and move on to Rio.
Oh, commenting. That's fun, I guess.